Okay, let's get started. So just another reminder, we have a no device policy in class, so no phones, no laptops. I've announced this earlier as well. Okay, so let's start with where we left off last time. Okay, so we were talking about virtualization, and just to recap, virtualization is essentially a mechanism that extends or replaces one interface and to uses it to mimic another one. Okay, so we talked about how you can do virtualization at the hardware layer, where you mimic one instruction set using another, at the OS layer where you can mimic one OS interface using the other, and at the application layer, okay, which allows you to use one library interface to mimic another library interface. And we talked about a whole slew of different tech mechanisms to do virtualization, and I was just getting into the details of hardware level virtualization. Okay, so this picture shows two different types of hardware virtualization. One is called type 1 virtualization, the other is called type 2. Okay. In both of these mechanisms, there is a layer called the hypervisor. Okay. The hypervisor is also referred to as the virtual machine monitor, or the VMM in literature. Okay. The terms hypervisor and VMM are interchangeable. Okay. And essentially that's the layer that is responsible for virtualizing hardware resources. Okay. That's the layer that exposes or allows you to create a virtual machine that looks like a physical machine. If you have more than one virtual machine running, it is responsible for resource management and resource allocation across VMs. You can do scheduling and all of those things. Okay, so we'll get into details of how we go about doing that in just a moment. But just to come back to this picture, there are two different kinds of hardware virtualization that you encounter. Actually, three. I'll talk about the third type in a couple of slides. There are two here that are listed. One is called type 1, the other is called type 2. Okay, what happens in type 1 virtualization, the type 1 hypervisor, is that the hypervisor actually runs on bare metal. Okay, what that means is you do not actually boot an OS on the machine. You boot the hypervisor itself. The hypervisor takes the role of what normally an OS would do. That's the thing that boots up on the machine. Okay? So when the machine starts up, you boot the hypervisor. It acts both as a kernel as well as the virtualization layer. So they are actually combined into one layer. Okay, so you are directly going to boot the hypervisor. There is no OS that's going to boot up on the machine. And then the hypervisor will allow you to create or expose multiple virtual machines. So here you can see two VMs. Okay. The first virtual machine actually is running Windows. Second virtual machine is running Linux. Okay. To each of those OSs, this looks like a real machine. Okay, the virtual machine just appears to be a normal machine, except that it's not a real machine, it's an emulation of a real machine, okay, using virtualization. Okay, so the OS here does not know about the presence of other OSs, it just it looks like it's running in a machine and that it controls completely. Okay. So you can create multiple virtual machines, because this allows you to take a physical server and create smaller virtual servers and run more than one OS on it. And the hypervisor will then be responsible for scheduling, just as the OS schedules processes and threads. In this case, the hypervisor schedules VMs. Okay? So you will take CPU resources and you will allocate time slices to VM. You can take the memory on the machine, partition it across the virtual machines and so on. Okay? That's type 1 virtualization. That is what you will find in servers, server class machines. Okay. If you have used virtualization techniques at all, okay, you probably use what is called type 2 hypervisors. Okay. So in this case, your machine will run its normal OS. When you boot up, you'll boot Linux or Windows or Mac or whatever, and you can run your apps on it as well. Okay. You can also start up a VM package that will actually incorporate within itself a type 2 hypervisor. Okay, so in this case, the type 2 hypervisor also allows you to create multiple virtual machines. Okay? But in this case, the type 2 hypervisor is running on top of what is called the host operating system. Okay? So the native operating system running on the machine is called the host OS. Okay, if you run a VM and you create another VM and run an OS in there, that's called a guest OS. So you will have multiple guest OSs running on a host operating system, each inside its own virtual machine. Okay, is that clear what I said? Okay, so essentially type 2 hypervisors run on a host OS, guests run inside VMs that are created by the hypervisor, and I will show an example. Okay, in both cases, okay, you essentially get a virtual machine that just looks like a physical machine. It's just what software runs underneath it is the difference between the two. Okay, so I'm going to show you an example. So this is a type 2 hypervisor called VirtualBox. Okay, if you've used, it's an open source software, you can download it. In fact, you will use it for your first homework very soon if you have not already done so. Okay, so you'll see here, I don't know how much this is visible, but you will see that I have in this case 4 different VMs. That is Ubuntu, okay, which is currently switched off, so I can just start it, and it will take a moment to start up. Okay, so you will see that that's a VM. The VM is actually running Linux, okay, on a Mac, and then this is now Ubuntu started up, and then you can actually use it like a normal OS. All right, so I just started. Let me just get rid of the messages. So you'll see that this is just a terminal, and you will. This looks like just like as if Linux is running on actual machine. You will see it's, but it's running inside a virtual machine. Okay, so anything you do on a real machine, you can do in this case as well. Okay, so my Mac OS X in this case is the host OS. Okay, VirtualBox is providing type 2 virtualization, type 2 hypervisor. I've created one VM. Okay, that's essentially running Linux. I can start another one. Okay, so if you want, you can boot a second one, right? So then now I have 2 VMs, each running its own OS running. So in this case, it's running. So I can just start this one, for example. Right? So you can create as many VMs as you want. It depends on how much resources you have. So you'll see that another one started up here, right? So and that's running another OS, right? So now you have 2 one host and 2 guest operating systems, right? So I'm going to shut this down, and then go back to the hypervisor. So you will see that when you create the VM, you can decide how much memory to give it, how much disk resources to give it. You will see that it has its own network interface card, which is a logical emulation. That's not a real Ethernet card. That's an emulation, software emulation of an Ethernet card, and you will have a virtual disk. It's not a real disk. A real disk is controlled by the native OS or the host OS, but it's a virtual disk. Okay, so this is all virtualized resources that have been provided to the guest operating system. Okay, so that's an example of type 2 hypervisors. Any questions here? Okay, so I'm going to give you more details of how all of this works. So now let's get into some details of how you can implement virtualization. Okay, so how do these hypervisors work? What are they based on, and so on. Okay, so this requires a little bit of understanding of. Okay, hold on for a second. Okay, so this requires somewhat of an understanding of how the underlying. Oh, not sure what's going on here. Hold on. Okay, it's very bizarre, but let's move on. So I'll explain some details of the hardware first. Okay, then you can understand how virtualization uses those hardware features. So first thing that you need to know about any CPU is that a CPU essentially has multiple modes of operation. Okay, any CPU, doesn't matter which one. At the very least, there are 2 modes. There's one called kernel mode, other called user mode. Okay. Now, what is the difference between these 2 modes? Is the following. Okay, so let's take all the CPU assembly instructions that are supported. Okay. In kernel mode, any instruction can be executed. In user mode, only a subset of those instructions can be executed. Okay, so for example, let's take the halt instruction. Okay, the halt instruction just halts the CPU. Okay. This instruction is cannot be executed in user mode. It can only be executed in kernel mode. Okay. And the idea is in user mode you run normal applications. Okay. And you don't allow normal applications to do things that might cause damage to others. So for example, you cannot allow a normal OS to execute halt and just halt the machine. Okay. Then anyone can write some code and put in a halt instruction and just shut the machine down. Okay. Only the OS is trusted to do that operation. So you can only execute those kinds of instructions in kernel mode. And there are many such things. There are instructions that allow you to change memory management information, page table mappings. You only allow that in kernel mode. And you can only allow I/O in kernel mode. So a whole slew of these instructions that you only allow in kernel mode, and in user mode you allow other things. Okay. So every CPU at least has these two modes. Okay. In particular, in Intel architectures, these modes are called rings. Okay, just a different term, means exactly the same thing. Ring 0 is essentially kernel mode. Ring 3 is pure user mode, where you can run untrusted applications and they'll only be allowed to do certain subset of things. Okay. Now in Intel you have more than user and kernel modes. You have two more modes which allow you to do more and more things. Okay. So for example, the ring picture is shown here. So the innermost ring is the red ring is called ring 0, kernel mode. Everything is allowed. Okay. The outermost ring, which is the green ring, is ring 3, which is user mode. Only certain things are allowed. Okay. And ring 1 and ring 2 allow you to do more things than what you are allowed in an outer ring, but less than in the kernel mode. So that allows you different levels of trust. So maybe you can run some system daemons in not ring 3 but ring 2, for example, okay, which will allow it certain more privileges than a user application. Okay. So that's something that every hardware will support. Okay. So, and then we will distinguish between whatever you can execute in kernel mode. So these we will call sensitive instructions. Because sensitive instructions are instructions that only the kernel can execute in kernel mode. Okay. And then there will be other instructions on your CPU that also allow you to cause a trap. Okay. These are called privileged instructions. Okay. So these are also instructions that, for example, if you have an interrupt, okay, or I/O, you can cause a trap. That's going to be, those are called privileged instructions. So here is a key result that allows us to understand how virtualization is going to work. Okay, so it says type 1 virtualization will be supported on any CPU if the sensitive instructions are a subset of the privileged instructions. So that basically means every sensitive instruction is also a privileged instruction. And you need to understand some details of why this is the case. Okay, first let me ask if everyone understands the difference between user and kernel mode and what's a privileged and sensitive instruction. Some architecture background is needed to understand that, but at least I define what they mean. Is there anything I should explain about the background before I try to explain the result?
Can you please explain privileged instruction?
Okay, privileged instruction is any instruction that causes a trap, okay, an interrupt. So if you have let's say you do a divide by 0, that can cause a trap. You try to do you dereference a pointer that points to an invalid address, that causes a trap. So any of those instructions can cause a trap. Many instructions can cause a trap. So you call any instruction that causes a trap to be a privileged instruction. Any instruction that can only be executed in kernel mode is called a sensitive instruction. Okay, so we want, essentially for type 1 virtualization, we want every kernel instruction or sensitive instruction to also be a privileged instruction. We also want it to be raise a trap. Okay, only in that case will we be able to implement type 1 virtualization. Why, we will see in a moment, but that's the result that tells us that you cannot just take any CPU and implement virtualization on it. Okay, so now let's ask the following question: why is that the case? Okay, so let me now explain what will happen in type 1 virtualization. Okay, so normally when you boot an OS on the machine, okay, the OS essentially runs in kernel mode. It has full privileges to do whatever it wants. Okay, I presume that's clear, right? Okay, the OS essentially has complete control over the hardware. It can execute any instruction it wants in kernel mode. Okay, now let's assume you are in the world of virtualization. Let's take this example in particular. When your machine starts up, you boot the hypervisor. The hypervisor is now in control, not an OS. The hypervisor is actually going to run in kernel mode and be able to execute all the sensitive instructions. The guest OSs themselves cannot be given full access, okay, because they are running inside a virtual machine. So in particular, you might actually run that guest OS as in user mode, okay, because the hypervisor is in charge. Anything else that's not in charge runs at a lower level of privilege. So in particular, let's assume it runs in user mode. Okay? But the OS does not know that. Okay, because you virtualized it and created this abstraction of a virtual machine, the OS believes it is still in control of the hardware. Okay, it believes that it has full access to whatever it needs to do. Okay, so any code that's in the kernel will still continue to execute sensitive instructions. Okay, but because it's in user mode, normally your hardware will not allow you to do that. Okay, because as far as the CPU is concerned, anything that runs in user mode is not to be trusted, so you cannot run any sensitive instruction in user mode. Is that clear? So now you are going to have a problem where the OS believes it is in charge, so it will continue to execute sensitive instruction like it would normally have. Because when you booted it normally on hardware, it controls the hardware. So it has rights to do whatever it needs to do for resource management. But in this case, you actually booted the OS inside a virtual machine. Okay? The hypervisor is the thing that's running in kernel mode. You cannot give full access to a guest OS. So it's going to run in user mode. It's going to execute your sensitive instructions. But then since the CPU is actually in user mode when that OS runs, those instructions cannot fundamentally execute. Okay, so how do we then make this work? Okay, so this is why that result helps, which says if a sensitive instruction actually triggers a trap, okay, so then what will happen is whenever the OS tries to do something privileged, okay, it's going to, let's say, it's trying to halt its virtual machine. It might execute halt. Normally, you wouldn't allow that, right? Because that's a user, from the hardware perspective, that's a user mode operation and you don't allow it. But if that's a sensitive instruction, if it causes a trap, the trap will cause the hypervisor to take over. Whenever there is a trap, you basically let whatever is running in kernel mode take over. Okay? So in this case, the hypervisor will take over. Okay? The hypervisor will figure out that your operating system is trying to perform a sensitive operation and it will perform it on behalf of the guest OS. Because the guest OS itself cannot perform that operation. When it tries to do it, it triggers a trap, the hypervisor takes over, the hypervisor does the right thing. In this case, it will halt the virtual machine, not the physical machine, because the hypervisor knows the guest OS is trying to execute halt. Okay, is that clear?
Is privilege instruction same as system call?
Privilege instruction is not the same as system call. System calls also cause traps, but system calls are not assembly instructions. They are user interfaces that are exported by the OS. Internally, they do cause a trap. Okay. So what they say, so in this case, the way we are going to let all of this work is type 1 hypervisors will run in ring 0, which is most privileged. Okay. You will run the guest OSs in ring 1, okay, not in ring 3. Okay, ring 3 is the least privileges. So you will run that in ring 1 and applications that run inside your guest OS will run at the least privilege in user mode, in pure user mode. Okay. So whenever the guest OS runs and it tries to do something privileged, you want a trap and you want that to work. Okay, so what that also says is you cannot implement type 1 virtualization on any hardware that you like. You particularly need any CPU that will only allow, or that will actually allow sensitive instructions to also cause traps. So that's the only way you can make this work. Otherwise, a normal Intel architecture will simply ignore sensitive instructions that are executed in user mode. They just ignore them. They don't do anything at all. Okay? So if you actually ran that on an older Intel CPU, okay, if your guest OS says halt, the CPU just ignores it as if that instruction was never even executed and you just move on. Okay, so the OS will essentially malfunction because it's trying to do something and the CPU is essentially ignoring it because it's in user mode, not in kernel mode. Okay, so essentially i386 architectures until recently ignored sensitive instructions in user mode. They did not cause a trap, they just ignore them altogether. Hence, you couldn't implement type 1 virtualization. You have a question there?
So then if like guest OS want to halt the CPU, does hypervisor actually halt the CPU? And what if that CPU is shared with another guest OS or something like that? How does that actually happen?
Okay, so question is, if the guest OS wants to halt the machine, then what happens? Because there may be other guest OSs and other VMs running. So halt is an instruction to halt the machine. That's your shutdown instruction. Okay? And when you execute halt, you're halting the virtual machine, not halting the underlying machine. Okay? The underlying machine continues to run other VMs. So in this case, this VM will halt. Okay, that machine will still continue to run, the underlying physical machine will still continue to run. So you have to interpret what that halt means. So this OS cannot actually halt the physical machine, it has no privileges. It only can do whatever it needs to do for its virtual machine. Okay, so that's the difference. Okay. So essentially what that says is that unless you have this property, you cannot implement that type of virtualization. And indeed, in early Intel architectures, you couldn't, because all sensitive instructions are ignored, until both Intel and AMD added extra hardware support precisely to support virtualization. Okay. So in Intel, you have something called VT. Okay, it's called virtualization technology. So you need a CPU that has VT features enabled on it. Okay, in AMD, you have something called SVM, which is the equivalent of AMD's implementation. Okay. What happens in both of these cases is essentially you can implement a bitmap. So it allows you to dynamically say, for these instructions, raise a trap. Okay. So for every instruction, you have one bit. Okay. When your machine boots up, if you turn on VT, you can then take all of your sensitive instruction and flip their bits, which will then essentially cause traps for those bits. Okay. So you can dynamically turn on this feature for any instructions you want using virtualization technology. So the hypervisor uses a hardware bitmap to tell the CPU saying, if this instruction is executed in anything other than ring 0, trigger a trap. So you can explicitly program your CPU to do that and get that property. Okay, VT is disabled, then you are back in this mode and then you can't actually run virtual machines at all. Okay? Any questions here? Okay, so here's a picture that I showed. I should have probably put the same picture earlier. So you have your hardware, which is the gray box. Type 1 hypervisor is acting as the kernel. That's your virtualization layer. You have one VM running here. Okay. In the VM, you have a guest operating system, okay, and then you have the circles are user processes. Okay. Type 1 hypervisor runs in kernel mode. The guest OS and applications don't run in kernel mode. In this case, we will let the guest OS actually run in ring 1, which is more privileged than its application. Okay. So whenever your guest OS wants to do any privileged operation, because of the previous property, you are going to trap to the hypervisor will perform that operation to you. This is exactly the same what happens when applications make system calls. Okay. System calls basically are a mechanism for an application to execute privileged operations that it cannot itself execute. So you call a system call and then the OS performs that operation for you. Okay. So in this case, some of these are also called hypercalls, as we will see. Okay. They are calls to the hypervisor. Okay, but this is being just done at instruction level. Okay. So this is essentially type 1 virtualization, and it is only run on server machines. Okay. We'll look at type 2 virtualization next. Any questions on this? Yes.
Suppose there are multiple virtual machines and they both, suppose there are 3 and they all 3 issue halt instructions. So the hypervisor, does it have kind of like a table to ensure and interpret that this instruction has come from the specific virtual machine and it will halt this machine?
Okay.
It's the same command.
So the question that is being asked is, whenever you execute a privileged or a sensitive instruction rather, can the hypervisor figure out which virtual machine triggered it? In particular, if multiple VMs all make the same operation, can it distinguish? That's your question, right? So clearly when you cause a trap, that trap is tied to a specific VM. Okay? The hypervisor will know exactly what's going on. You could have asked what you asked for an OS, saying if three processes all call read to read a file, does the OS know which process called which read? Okay? The OS has to basically, it's completely tied to a particular invocation. The same is true here. Okay, when you are invoking this, you will have call a trap handler. The trap handler will know what VM in this case invoked that trap. Okay? So if there are multiple traps all occurring at the same time, even if for the trap for the same instruction, you can distinguish.
And as for the read one you said, what I'm trying to ask is this is something in the hypervisor that maintain a table, some kind of mechanism which identifies which processes and which VM called it.
There is no need for a table. The trap handler knows who's invoked it. Right? This mechanism is exactly the same mechanism that's used to implement system calls in an OS. Okay, the way system calls are invoked is they also cause a trap which allows the kernel to take over and execute the system call. It's exactly the same mechanism being used in the virtualization context. So you have to always be able to associate a trap with whoever invoked that trap. Okay? It doesn't matter what the trap is. That's exactly what you're asking. You don't need a table. You don't need a table to do that. The trap handler can figure out who invoked it. Okay? So it's associated with a specific VM in this case. Yes, question.
So when an application is running in the guest OS, it would let's say calls a system call, then there would be interrupt on the guest OS, which
Yes.
would then make a trap on the hypervisor.
Okay. Question is when the application process makes a system call to the guest OS, that's going to cause a trap inside the virtual machine. Okay? So the guest OS will take over and try to execute that system call. In most cases, that system call itself will require you to execute some sensitive instructions. For example, if you are doing I/O or some such thing. So when you try to execute that instruction, okay, that will transparently cause a trap into the hypervisor. Okay? The guest OS does not know that's happening. It just thinks it's executing some assembly instruction on the CPU, but because it's not allowed, okay, this hypervisor takes over and executes those instructions on its behalf. Okay, so
It's very expensive, traps all the time.
if you have traps all the time, the question is it expensive if you have traps all the time? That is the only way you're going to make things work, and this is why virtualization always adds some overhead. If you ask someone, they'll say, if you add a virtualization layer between the OS and the application, it adds overhead. This is why all these overheads come in, because there are multiple levels of processing you have to do to perform a particular operation. Okay? Yes.
To get true parallelism, if I want to spawn a kernel level thread, so does that thread stand in the virtual kernel mode or in the hypervisor kernel mode?
Okay, so let me rephrase your question. The question is, if you wanted to support kernel level threads, okay, are those kernel level threads dealt with at the guest operating system level or at the hypervisor level? Is that the real question, right? So the way to think about this is what is running inside that entire VM, like shown in this picture, okay, is not visible to the hypervisor. Hypervisor thinks that whole thing is one process. Okay. The fact that there may be 10 applications running in them are not explicitly visible to the hypervisor. The guest OS is going to take care of managing its OS. Okay, there's abstraction boundaries here. The guest OS thinks is running on a real machine, although it's actually running on a physical machine. It's going to deal with all of its applications. Okay. The hypervisor does not actually know how many processes may be running. To it, it just looks like one blob that's just executing. Whenever you run the guest OS will then schedule its application and so on. So the kernel, going back to your question of kernel level threads, the guest OS is given illusion of virtual CPUs, not physical CPUs. Okay. So there are vCPUs which are then mapped in some way to the underlying cores. Okay. So essentially whatever is executing inside the guest OS run on virtual processors, not on real processors. The virtual processors may have arbitrary mapping to physical processors. Okay. So in some sense a type 1 hypervisor does not deal with threads that may be inside processes inside a VM. That's too much of breaking layers of abstraction. Only the guest OS will schedule the kernel level threads on virtual CPUs. Okay. The hypervisor will schedule virtual CPUs on physical CPUs. So whenever that happens, the thread will actually run. Okay. And neither of them know that what is happening above it or below it. Okay. That's sometimes there's an abstraction boundary there. Okay, any other questions? Okay, so I'm going to show you what happens in type 2 hypervisor. Okay, so if you go back to what I said here, okay, you'll see type 2 hypervisor, which was the virtual box example I showed you, has a guest OS that's running in a VM. The VM is actually running on a host operating system. Okay, so now we have one more layer that you added because you actually boot your normal OS. VirtualBox runs as an application on top of your normal OS. Okay, so in this case, the hypervisor is not in charge of the hardware. It's your OS, if it is Windows or Mac that you booted, that's in charge. Okay, so in this case, the hypervisor is what was in charge. It controlled access to the hardware. Here, your native OS, which is your host OS, in charge. Okay? Hypervisor runs as a normal application. Okay? The guest OS runs as a VM inside the hypervisor. Okay? So there are multiple layers of abstraction that you need to deal with. Okay? So you could ask the same question. The guest OS still believes it's running on a virtual machine, that it owns hardware. Okay? It is going to execute sensitive instructions once again. Okay? That those sensitive instructions are going to run in pure user mode. Okay, in this case, tapping to the hypervisor makes no difference because the hypervisor has no control either. The hypervisor is also running as a user process. Okay, at least in this case, the hypervisor actually ran on hardware. There's no other layer, so it controlled everything. So you cannot use the same mechanism you used in type 1 hypervisors in this case. Okay, so the way most of these things work is the following. Okay, so the VMware example or VirtualBox example is the following. When you load your guest OS, okay, your virtual machine hypervisor, which is your type 2 hypervisor, is going to scan the OS code. Okay. Every time it finds sensitive instructions, okay, it will dynamically do binary translation. Okay. Essentially, you can think of whenever it finds a sensitive instruction, it will inject a function call there. Okay. The function call will simply make a function call to the hypervisor. The hypervisor can then make real system calls to the underlying OS to perform the privileged operation. Because the only thing that can actually perform privileged operation in this case is the host operating system. That's in charge. Okay. So this requires even more overhead because as the OS is executing, okay, you are actually scanning assembly instructions that the OS is about to execute, and if you see that it's soon going to execute a sensitive instruction, you will replace it with an equivalent other instruction that will basically make a function call into the type 2 hypervisor. The type 2 hypervisor will have a function implemented for every instruction that could be executed. So for example, if it's halt or IO or whatever, you will basically then implement them with real system calls. Okay? And that has to happen on the fly. Okay? You are scanning code as it's executing, okay? And performing the binary translation. Okay? And to ensure performance, you have to make sure that you do not impede execution of the guest OS. Otherwise, you will slow things down substantially. Is that clear what I said? Okay. The other important thing that goes with it is you no longer have a need for sensitive instructions to cause traps. Okay. Because I said type 1 hypervisors, the sensitive instruction need to cause trap. That's a hardware feature you are depending on. In this case, you are getting rid of sensitive instructions altogether by simply injecting function calls whenever they execute. Okay. So you are not depending on any hardware features, you are going in and replacing all of those instructions with essentially function calls on the fly or just binary translation. Shouldn't say function calls, a set of equivalent other assembly instructions that invoke the type 2 hypervisor and ask it to perform some privileged operation. So now what this says is sensitive instructions are replaced by procedures that emulate them. As a result, sensitive instructions are not even being executed by the guest OS. As it's being executed, you are replacing them on the fly, so you don't need any hardware features. What that also says is you can take things like VirtualBox or VMware or Parallels and run it on any CPU. Even old Intel CPUs can run these type 2 hypervisors without any hardware dependencies. Okay? That is why for the longest time you could actually run desktop based virtual machines on any machine, But if you actually went and tried to boot a type 1 hypervisor and it's an older CPU, it wouldn't work because it needed VT support. Okay, is that clear? Yes.
So like when we use VMware Player, for example, it asks you to enable intent VT if it's disabled.
Yes. So the question is, if you run VMware, it asks you to implement VT support. All this is saying is you don't need it. If it is there, you can take advantage of it.
So what are the advantages, like a type 2 hypervisor can take of Intel VT?
Okay. So question is, how does type 2 hypervisor take advantage of virtual machine? So in that case, what you can do is you don't need to scan and trap. Okay, you can essentially allow it to cause a kind of trap that the hypervisor can catch and then invoke system calls. Similar to what a type 1 would do. Okay, so you can, so that will reduce the overhead. Otherwise, we're actually scanning code just before the OS is executing and doing this on the fly.
So the binary translation step is
The binary translation could potentially be skipped if you can do it for all of them. Okay, so some question here? No. Okay. Okay. So that's type 2 hypervisors. And then,
What is that cache modified block?
okay, so cache modified. So this is all binary translation. I have no idea why this is happening. Okay. So the binary translation happens using a code cache, where the type 2 hypervisor will load the code that the OS is going to execute. It's going to scan it and cache, replace those instructions, and then the OS will just transparently execute them. Okay, that's just how binary translation is actually done. Okay. So next and the last type of hardware virtualization is para-virtualization. Okay. And when I introduced para-virtualization last time, I said the assumption we will relax for para-virtualization is we are now allowed to run a modified OS that's built for virtualization. In the previous two cases, you could take an unmodified OS that's designed to run on real hardware and simply run it inside a virtual machine. You don't need to change the code at all. Everything runs as is. Okay? But you need either hardware support if you are type 1, or you need to do binary translation, which slows you down if you are in type 2. Okay? The question is, can we get around some of these limitations? Okay? And the way we, now if you are allowed to change the OS, not the application still run unmodified, but you are allowed to boot a special version of Windows, let's say, or a special version of Linux. What could you do that will help us avoid some of the drawbacks of, let's say, type 2 virtualization or type 1 virtualization? So how could you get around the restriction that sensitive instructions have to cause a trap? So say you are a kernel designer and you are told this VM kernel or this kernel is actually going to run inside a type 1 VM. Okay? But you don't want to depend on hardware features to make it work. What are the things you have to do? Okay, you have to get rid of sensitive instructions because they will no longer work if you don't want them to run on CPUs that don't cause a trap. So what you will do is you essentially will take the kernel code, you will look for any function in the kernel that calls a sensitive instruction and you will explicitly replace it with a hypercall. This is what type 2 virtualization did on the fly. Whatever you did for binary translation, you will actually change in the code itself and recompile the kernel. So why do it over and over again while the kernel is running? Why not build a version of the kernel where you take every instruction and actually write a function call to invoke a type 2 hypervisor, a type 1 hypervisor? If you do this, you have what is called para-virtualization. So in this case, you are going to run this modified kernel that's specially built for virtualization, where you have gone and replaced every sensitive instruction with a hypercall. Okay? This is what type 2 was doing on the fly. Now we just go and change the kernel and run it on type 1. So in this case, so you have a modified Linux here. So in this case, you are actually trapping on sensitive instruction. You no longer do that. The Linux, whenever you want to perform a sensitive instruction, the OS will actually make an explicit call to the hypervisor, which we'll call a hypercall. Just as you made system calls to the hypervisor, you make hypercalls and tell the hypervisor to do something for you. Okay. So this is referred to as para-virtualization. Okay. So early type on hypervisors used para-virtualized kernels because the hardware did not support them. Okay, so if you have Zen VM, which is now still supported in Linux today, that was a para-virtualized kernel. VMware ESX server was a para-virtualized kernel. With modern hardware, you no longer need to do this, okay, because the hardware supports all of this. You don't need to change the OS. But if your hardware doesn't support something, then the OS has to be modified. So those are all the trade-offs you need to make. Okay, any questions here?
Is hypercall and interrupt kind of thing for hypervisor?
The hypercall will cause an interrupt. It's doing exactly the same thing. System call cause traps to OSs, hypercalls call traps to hypervisors.
What is the difference between trap and interrupt?
Okay, what's the difference between a trap and an interrupt? So you should think of a trap as a software interrupt. Okay, so interrupts are by definition hardware exceptions. Traps are software exceptions.
Given the case, whether it is para-virtualization or type 1 virtualization, we'll be having interrupts, right? What is the getting? Gain or something we are getting?
So are you asking what's the difference in performance between the two? So there is, in both cases, there is no real difference in performance because both of them cause a trap. Okay? The only thing that has happened is you are basically using an idea from type 2 hypervisor and implementing in type 1 by modifying the kernel. So that's the main difference between the two. It's not a performance difference. Okay, so that's type 1 virtualization, type 2 virtualization and para-virtualization, and they all have to deal with virtualizing the CPU. Okay, we only talked about CPU so far. We haven't talked about what happens to memory, what happens to disk, what happens to the network and so on. All of those resources also have to be virtualized. So I'm going to quickly run through how memory management might work. Okay, so again, you have the same problem. Okay? The OS is running inside a virtual machine. The OS believes it is in charge. So it thinks, for example, it can change the memory management information like page table mappings can be changed, is what the OS would believe. Okay? Some of that requires you to perform sensitive operations. Okay, so you have the same problem. If the OS tries to change page table mappings, it does not have the privileges, so the hypervisor has to do it on behalf of the OS. So the way many virtual machines work is the hypervisor keeps track of a second page table called a shadow page table. Okay? The OS keeps its own page table. The OS doesn't know and never knows it's actually running on a virtual machine. It's all transparent to the OS. So the OS might actually try to make some changes, okay, and then the hypervisor keeps track of those page table mappings that will cause a trap, okay, because it is a sensitive instruction, and then you modify the shadow page tables which are then reflected into the real page table. So the OS is essentially going to change memory management information on behalf of the guest operating system, because the guest operating system does not have the privileges to actually perform those changes. So you use a similar idea that you used in the previous case. Okay? And you have this notion of keeping track of mirrored page tables or shadow page tables inside the hypervisor to change the mappings whenever the OS asks you to change them on behalf of the OS. Okay? So there are a lot of details of how that works, but I won't go into them here because it requires you to understand details of hardware again. I just want you to know the high level idea. It's the same as before. Okay, the OS, to change memory management information, you have to execute sensitive instructions. The guest OS does not have the privileges, so the hypervisor helps the guest OS by keeping track of additional information and changing it on behalf of the guest OS. Okay, so that's the basic idea. Okay, so now as far as IO virtualization is concerned, that's a little easier to understand. Okay, so again, in this case, the guest OS thinks it will manage a disk and it will manage a file system on the disk. Okay? The real disk is actually managed either by the hypervisor in type 1 or is managed by the host OS in type 2. Okay? So you can't let the guest OS go and start mucking around with files that are not controlled by it. Okay? So what is going to be done in this case is you are going to provide the abstraction of a virtual disk. The virtual disk will be implemented as a large file on the physical disk. Okay? So in other words, your guest OS is not going to get access to the real disk. So you will basically give it access to a large file, which the virtualization layer will make it look like a real disk. So when you try to read and write to a virtualized disk, underneath the hypervisor will just read and write data to a large file. Okay? The OS will not know that that's happening because that's all hidden from the OS. That's happening, that's being done by the hypervisor. Okay? So your virtual disks in most cases will be just implemented as large files on a physical disk, and you basically read or write through these large files exactly the way you would read or write blocks to a virtual disk, a physical disk. Okay? So that's the abstraction that's going to be given, and I will show you some examples. Okay, so let's see. So if you look at that Ubuntu VM that I had booted, okay, so the virtual disk is a VDI disk. Okay, you will see that's a 4.6 gigabyte file on a physical disk. Okay, so that actually contains all of the data and the files that the Linux operating system, when it boots up, is going to read and write. Okay, to the native OS, it just looks like a large file. Okay, when the Linux boots up, it's basically going to read or write from that file, and it'll just look like a disk that's 4 gigabytes inside. So smaller than a physical disk, but you can make it as large or as small as you want. Okay. So now the fact that this disk is actually a file is hidden from Linux. When it boots up, you will actually look like a real disk. Okay, as you can see, we'll start it up again. Okay, so if you look at this, so you will see that the root partition is about 3.6 gigabytes in size. Okay? All of the data in root and all of these files are actually stored on that virtual disk file that I showed you in the underlying file system. Okay, so you are actually reading and writing from that file, but to the OS, it just looks like you are reading and writing to partitions on disks and so on. Okay, so the fact that you are reading or writing to virtual disk is not material, it just looks like a real disk as far as the OS is concerned. And the virtualization layer is making those translation. Whenever you read or write, you actually translate that to read and write to parts of that file. Okay, so this is how you are going to provide a virtual disk abstraction to a guest OS. Any questions on this? Same is going to be done for the network interface card. Here's your question.
Does this give us the advantage where we can resize without repartition?
Okay, so the question is, does this give us an advantage where you can change the size of the disk without repartitioning? So you can, in a virtual machine, make the virtual disk bigger. Okay, then the partition size will also grow. Okay, that needs combination of virtualization techniques and the OS to be able to handle things. But yes, you could make it bigger. So you will see that the way you will actually so I don't know if this is visible, but I'm going to make that a little bigger. So we'll see that there is a logical network card here which is called VBoxNet0. Okay, that's the network card that the guest OS is going to manage. That network card is then mapped onto the actual physical Ethernet card for communication. Okay, again, so you create logical Ethernet card, which are emulated cards, are just software emulations of actual network interfaces. The guest OS reads or writes data from the logical card. The logical card is then mapped to the physical card either by the type 1 hypervisor or by the guest OS or the host OS rather. Okay, so you are going to emulate all these pieces of hardware as far as the virtualization layer is concerned. Okay, is that clear? Any questions here? Okay, so that's I/O virtualization. We already talked a little bit about this. So I'm going to say a little bit about virtual appliances and whatnot, and then we will move on to OS level virtualization. Okay, so one of the many benefits of virtualization, okay, is that you can download a pre-packaged VM. Okay, you can certainly create a new VM which is a blank VM. You can install an OS in it, you can install your applications and run. Okay, just as you would install an OS on a physical machine. Okay. But one of the advantages of virtual machine is someone else can do all of that for you and then just give you a large virtual disk. Then you can just boot out that virtual disk and all the OS and applications have been pre-packaged and pre-configured on that virtual machine. Okay. So this is referred to as a virtual appliance. Is one way by which you can distribute pre-configured pieces of software with the OS. So you don't have to download some application and install it and configure it. You just download a virtual machine which is called a virtual appliance. It has a OS already installed in it. It has the application you are looking for already installed in it. Okay? And you can just run it, and all of the configuration overhead that you as a user or system administrator would have to perform is no longer there. Okay? So you can go to VirtualBox or VMware Marketplace, and you'll see that lots of the developers and users have pre-configured virtual appliances deployed there. So you can just download one of them and run it. Okay, and then you basically can try out a piece of software without having to perform all of it. So it simplifies software distribution. Okay, that's one advantage of doing this. Okay. The other thing I wanted to mention is if you actually have more than one CPU cores or CPUs on your machine, okay, you can also do more sophisticated things which I did not show, which allows you to dedicate cores to certain VMs and whatnot. Okay, if you have 4 cores, you can say take these 2 cores and allocate it to VM1 and take this third core, allocate it to VM2. So you can do this mapping from virtual processors to physical processors. Normally, a hypervisor will simply use a scheduling algorithm, like a CPU scheduler. It will use a VM scheduler to schedule VMs. Okay? But you can also dedicate cores to VMs by just hardwiring it, saying whenever this VM runs, it should run on these cores. In that case, there is a static mapping between a virtual CPU and a real CPU. Okay? Normally, you would actually have scheduling that will take care of that for you. So there are all these advanced features which actually make it very easy to use in many different contexts, okay, including cloud computing. Okay, cloud computing uses all of this virtualization underneath. Okay, when we come to it, you will see how some of these ideas can be used. Okay, yes?
You mentioned that each guest OS is like a process running. In that case, the memory of that virtual machine will be the address space of the process.
Okay. Question is each guest OS is like a process, and what's the memory that's allocated to that guest OS? Okay, is it like a process address space? That's it.
How will it prevent it taking a large number which is of another guest OS?
Okay, so the question is about memory allocation. So when you go back to the VM, okay, when you configure the VM, okay, you basically allocate some RAM to it. So you'll see that this VM has 512 megabytes of RAM. Okay, so you essentially are constructing a software PC. Just on a hardware PC, you put in, when you buy it, you configure some RAM, and that's the amount of RAM allocated to it. When you create a VM, you can say how much RAM do you want to allocate to it, and you can allocate any amount up to the actual physical RAM on your machine. So when your VM boots up, okay, your hypervisor is going to dedicate that much memory to that VM. Okay, so you are not, unlike a process where the memory will change dynamically. In this case, you can pre-specify how much memory you want to give to a VM. And that's the amount of VM memory that the guest OS has to work with. So when the guest OS boots up, it will look like the physical machine has 512 megabytes of RAM in this case. And that's what it will manage. Okay? Now there are more sophisticated techniques where the hypervisor might pretend it's giving 512 MB, but it might give it less and give it more on the fly, just as you do process memory management. But that's a separate matter. The simple approach is you basically dedicate some amount of RAM and that's it. You don't change it.
So when I run htop on this host machine I see one process with 512 RAM being taken.
If you actually run, if it is hardwired, you will see 512 MB of RAM. As I said, in many cases you can do more sophisticated things where you can say I've given it 512, but if it's not using it, I don't have to allocate it. I can swap, I can do virtual memory management, etc. But that's a separate matter. Yes, one question.
So when I'm not using the VM anymore, so will that memory which was allocated before, will that be freed back for my host OS?
Yes, so question is if you are not even running the VM, will the memory that's allocated to you freed? So that is indeed the case. Okay, this allocation is only in place when the VM is actually running. Okay, otherwise you don't need to dedicate that to the VM, it's just free memory as far as the machine is concerned. Yes, question there.
In I/O type 2 virtualization, suppose there are two requests for a printer by virtual OS and the host OS. So is there any preference given to host OS?
So you are saying if there is a job being printed from a guest OS and a normal application, is there a preference? There is no such preference. You could specify priorities if you want, but as far as the native OS is concerned, two jobs have come in. Okay, one came from a real application, the native application, the other came from an application running inside a guest OS. So there is no such preference given as far as I know. But I mean, of course, you could construct ones where you could prioritize if you wanted to for some reason. Okay, all right. So in the remaining 20 minutes or so, I will talk about OS virtualization. So this is a completely different technique altogether. Okay. In hardware virtualization, we actually had to emulate a real CPU, a real disk, a real network card, and RAM. Okay? And then somehow take those emulated resources and map them to actual physical resources on the machine. In OS level virtualization, you are essentially using the system call interface of the OS and exposing another system call interface. Okay, so here is the picture that will tell us the difference between the two. Yeah, so you can think of OS virtualization as lightweight virtual machines. Okay, the reason it's lightweight is you will see inside each of these virtual machines you do not run another OS. In the previous case, inside each VM we actually ran a guest OS and then applications ran on top of the guest OS. In case of OS level virtualization, you are not running a OS in here, you are directly running applications, and the underlying host OS provides whatever OS services those applications need. Okay? In other words, the guest OS is actually the host OS itself, so you don't need to run another OS. Okay? But you get all the other benefits of virtualization, which is you can say this container is given so much memory. Okay? It will then use a logical network interface card. Okay, all of what we did as far as resource management and resource allocation is concerned can still be done here. Okay? But you do not actually run a full-fledged OS inside your OS level VM. Okay? This is why it's more lightweight, because you don't have layers and layers of OSs running. There's only one running that provides all the services, and these applications essentially run inside a container and talk to this underlying OS. Okay? Now you could ask, what did we gain by this? Why could I not have simply run these three applications as applications on the OS? Why should I put them inside a container?
Sandbox and separate.
Okay, so you can do sandboxing. We'll talk about that. Anything else?
It's safer.
Sorry?
Safe.
It's safer. Okay. So there are many reasons you want to use OS level virtualization. As was mentioned, it gives you the ability to isolate other applications. So what happens as a result of this container is these applications can no longer see these other applications. So if you run PS or top or something that tries to list all the processes running, you only see the processes running inside that container, that the fact that there are other processes running on the machine is now no longer visible. Okay? Same is true of the virtual disk. Okay? You can actually restrict the part of the file system that's accessible to this container. Other files on your disk are not even visible. If you run a normal application, the entire file system is visible so long as you have privileges. to read or write files. In this case, you only give access, you can give access to part of your file system subtree. So you can isolate these applications from other applications, you can isolate what files these applications see, you can do more fine-grained resource allocation. So there are many benefits to still putting the application inside a lightweight virtual machine. And in the Linux world, they are called containers. Okay, containers essentially mean an OS level VM. Okay, that's just a different terminology. Okay, so no hypervisor, the OS is actually going to provide all the support that the application needs. Okay, so here are two examples of this is the Linux world where your containers, that's the Solaris world, but it's effectively the same thing. Okay. Now the other thing that I did mention, okay, so isolation is one advantage. The other thing is because you are emulating one interface using another, you can pretend inside this container that the OS that's running underneath is actually a different OS, an older OS, for example. So maybe this is Linux version 4. Inside this container, you can provide the illusion that that application is running on Linux version 3.2. Okay, and then this interface, a system call interfaces from 3.2 will then become accessible. Okay. So this is another advantage, which is backward compatibility. You don't have to change your applications if the OS changes. Okay. You can run it inside a container and provide the illusion of an older system call interface. Okay. That is essentially what Solaris does. Okay. It has these zones. Inside each zone, you have to not only say give it so much memory and so CPU resources and whatnot, you also have to say which version of the OS should be visible to the application. So you can give any version from the current version to some previous version, and then the zone will emulate an older version. Yeah, that's what virtualization will do for us.
Like Rosetta on Mac.
Okay, so question is this like Rosetta on Mac? Rosetta is an application level virtualization, not an OS level virtualization. It does binary translation from one architecture, which is PowerPC, to Intel. Here we do not pretend as if these are other architectures. It's the same OS, same hardware. You're simply getting isolation benefits. Okay? So different layer of virtualization. Alright, so let's now see. So there are many OSs that all do this. Okay, in Solaris they are called containers. In Linux also they are called containers. In BSD they are called jails. Okay, so you can jail a process or a group of processes in a container or a lightweight virtual machine. Okay. This picture, which I don't know if you can read everything, illustrates the difference between type 1, type 2 and container virtualization. Okay, so in type 1 virtualization, the hypervisor runs on hardware. Each of these black boxes is a virtual machine. You actually run an OS inside each virtual machine. They could be different, and you run your application. Okay, that's type 1. In type 2, okay, which is what we showed you here, you just run your normal OS. Okay, you could run Mac, for example. Okay, then you start the process, which could be VirtualBox, that's essentially a hypervisor, and then you have VMs, and then there's an OS running inside them. Okay, so there are three layers here. The native OS, which is the host OS, there's the hypervisor layer, and an OS, which is a guest OS. Okay. And this essentially is the OS virtualization, where you just have an OS that you boot up, you create a container, and then you just simply run your application inside the container. And there is no extra OS you run there. That application simply uses the underlying OS services. So you will see in terms of software overhead, you substantially reduced it in that case. Okay. Now, there are less, there's some trade-off there in terms of getting less isolation. So for example, in either of these two cases, if the OS triggers a kernel bug, the kernel will crash. Right? So you can cause some, do something and cause your machine to hang, for example. This may happen to you. Okay? And if one machine hangs, it does not impact anything else. Right? So this VM will continue to run even though this OS may have hung the VM. Okay? You do not get that benefit here. If one container triggers some bug in the OS and causes the OS to hang, all other containers are impacted. Okay? Because the OS is shared by containers. So you are a degree of isolation, you do get isolation, but it is not as strong as what you would get in case of hardware virtualization. Because here these are independent machines themselves, they are not related to one another, So you can cause an OS to malfunction, it doesn't impact other OSs. Okay, there you do not get that benefit. Yeah, because the OS services are shared. Any questions here? Okay, so you get many benefits. Fast provisioning is much faster to create and boot a container than it is to boot a VM, because here you have to actually boot an OS inside the VM. Here you simply create the container and just run the app, whatever application you want inside the container. Much faster to start up. Okay, you get native performance. Because your OS is actually, there's no real virtualization in terms of doing any translation. You're actually running on native hardware. Okay? You're simply isolating the containers from one another. Okay? And then just not allowing each container to see what's running inside other containers or on the native machine. Okay? So that's essentially another advantage, and it's lightweight because there's less overheads in this case. Okay? So those are all the pros and cons. Any questions on this? Yes.
So you said that for memory management, there is only one, like in the running process, you will see only the one container being run. So how is the memory management working for that? Does the container judge what memory is required by the internal applications and then give a request to the host OS to get more memory?
Okay, so the question is, how is memory management going to work for containers? Does the container figure out how much memory needs to be given to these applications and then tell the OS? So you can do it differently, it depends on the OS platform itself. You can, just as you could dedicate RAM to VMs, you can dedicate RAM to containers. Just as you could dedicate cores to VMs, you can dedicate cores to containers. Okay, so you can say this container needs to be allocated 2 cores from the underlying hardware and it needs to be given 1 gigabyte of RAM, and then the OS will respect that allocation. Or you could say do this dynamically, schedule the processes any way you want. Schedule the processes any way you want. Let the OS figure out how much RAM to give to the processes. Okay, so you have many different kinds of resource allocation methods that could be brought to bear, and you could, depending on what the needs are, you can configure the containers appropriately. Yeah, so that brings us to some of these issues that were mentioned. So there are many mechanisms in, so LXC stands for Linux containers. So I'm going to do a quick case study of Linux containers just to give you some flavor of how OS virtualization works. Okay, so there are many mechanisms that you can use from the underlying kernel or kernel extensions to implement LXC. Okay? So one is called namespaces. So this gives you process-based isolation. So you can say you can say only these processes can see each other. Other processes cannot see each other. Okay? So that's the notion of what's called a C group or container groups. You can also say only these files are visible. Okay? These other files are not visible. So there's a mechanism in Linux called change root, which basically changes the root directory to be any other directory in the system, and then you can only see that part of the subtree. Okay? So Linux containers use some of these mechanisms to provide isolation. So you can hide certain files, you can hide other processes using this OS level mechanism. Okay? That is what is used to implement. You can also, C groups have this notion of limits. That was exactly the question that was asked. In a C group, you can specify limits, saying 1 gig of RAM, no more. Okay? Give it 10% of the CPU. Or you could say give it 2 cores. Okay? You can specify it in many different ways. So you can specify this resource limit that tell the OS what is it that you want to give to this container. Okay? That is done through this C group interface, okay, which will basically allow, you can also set priorities for containers. Okay, and then that is going to be taken into account by your CPU scheduler when it schedules processes inside that container. Okay? So these are all standard OS level mechanisms that now you are using in a container context. Okay? And there are many of these mechanisms already inbuilt into the Linux kernel for many other purposes that are actually being used in this case. And some are specifically designed for containers themselves. Okay? So those are some mechanisms. I will also mention, so there are also security modules and access control which I will ignore, but I do want to mention Docker, which you may have heard of or used. Okay, so Docker essentially uses Linux containers as its underlying technology. Okay, Docker is built on top of Linux containers. So any Docker machine that you run is essentially running as a container inside of Linux kernel, on the top of the Linux kernel. Okay, so I will show you some examples as well. Okay, so here is a lot of details about Linux namespaces, which is essentially the ability to restrict what a container can see, and basically, so in this case, processes will have the illusion that they are the only processes in the system. Okay, so if you log into a container and then just do ps or top, you will only see the processes that are inside that container. Those processes cannot see some other process that's running. Okay? You will essentially not be able to see it. So this notion of a namespace says which process names are accessible to you. Okay? So you can restrict that to that mechanism. Okay? You can change mount points and which PIDs are visible and so on. You can also do this as a user level. Okay? You can say only these users are valid users inside the container. So you might have 5 users with accounts on the machine. You can say only these 3 users can actually even access the container, and then the other users cannot even log in. It will look like those user accounts don't exist inside that container. Okay, so you can actually do user level access control as well. So there is a lot of flexibility that these mechanisms actually provide. Okay, they are all used in this context. Okay, this picture is hard to see, and I'm just going to ignore it because it's not important. All the details are here. Yes.
So since you mentioned users, do the containers internally have user-specific application data? Like if you have directly users on the host OS or
Yes.
Linux, it's partitioned differently.
So question is, do containers have access to user data? Okay. The assumption or the right way to configure it is if you have.
Do the applications inside the container, are they as well partitioned to support multi-users?
Right. So question is, are the applications designed or partitioned to support user? That's your question. Right? Or are they able to support users? Can they access user directories and so on? So that is how you are going to configure a container. Yeah, so you can say only these users can access it. Only these home directories are visible. Other home directories are not visible. And then when a process runs, in the end, a user has to start a process. So users can log into container just as you can log into any machine. Okay? So at the end of the day, it still looks like a VM. So you can log into a VM and you can start whatever processes you want. And whatever privileges have been given to the container limits what you can and cannot do. Right? So you can say only these applications can be run by users. These other applications cannot be run. You can restrict it that way. Right? Any other questions? Okay, so now I'm going to give you a little bit more detail about how CPU is allocated across containers. Okay, and this will go back. So this mechanism is implemented in the Linux C group, but let's not go into the details of C groups. Instead, I'm going to focus on the mechanism. So a few classes ago, we talked about lottery scheduling. Okay, you will remember that we said we can give a process some number of lottery tickets, and the proportion of CPU you get is, or the amount of CPU you get is proportional to the number of lottery tickets. Okay. So lottery scheduling is a class of, belongs to a class of scheduling algorithms which are called proportional share schedulers. Okay. What these schedulers do is they allow you to allocate some proportion of a resource, say a CPU, to a given application. Okay. And that is what is actually used by these mechanisms. So essentially now what you will do is every container will be given a weight, let's say Wi. Okay. And the CPU scheduler that will run on the native host kernel will do proportional allocation. That means if there are 2 containers that are weight Wi and Wj, the CPU allocation will be in proportion Wi is to Wj. In other words, you give each of them weight of 1, this is going to get half and this is going to get half. Okay. Or you can say this gets weight of 2, then this is going to get 1/3 and 2/3. Okay. So there is a whole class of algorithms. So lottery scheduling did exactly that in a randomized fashion. Okay? There are deterministic schedulers that do the same thing. They actually look at the weight, and based on the weight, they'll say, okay, every time I give one time slice to this container, I have to give 2 time slices to this other container. So they will do that in a deterministic fashion. So those schedulers are referred to as proportional share, weighted proportional shared schedulers. And this class of scheduling is called share-based scheduling. You use a weight to allocate a share of that resource. You can do the same thing for the network interface card, which says if you have a gigabit card, take the bandwidth on that gigabit card and partition it based on weights. You can say this container gets weight of 1, that container gets weight of 2. So you get 1/3 of the bandwidth, incoming, outgoing bandwidth is allocated to that container and 2/3 to that container. So exactly the same mechanism can be used whether it's CPU or the network card, for example. Okay. So that share-based scheduler, you can also have what are called hard limits. The hard limits is a dedicated amount. Okay, so you can say 30% of the CPU is given to this container. Whether it uses it or not, at this point you have done a hard allocation. Okay. Mapping a virtual CPU to a core is also a hard allocation. You say you are given a core, whether you use it or not, no one else can use it at that point. Okay. So in these cases, these are soft allocations because they say if this process doesn't use it, the CPU will be allocated to some other process. You don't waste CPU cycles. Okay, so these ones are hard limits. That is also allowed. Okay. And then there is another class of scheduler that's credit based that say I am given a share. If I don't use my share, I accumulate credit. Saying I had one time slot, I have decided to give it to someone else, but I basically get a credit for one time. So I can accumulate credit over time, and then at some later time I can use up all my credit. Right? So those are called credit-based schedulers. So you are given one time slot, you can use it or take a credit and use it at a later time. Okay? So you have this whole slew of different scheduling algorithms. Okay? Within each you will see there are maybe 10 different variants. If you actually go read the papers, you don't need to for this class, I'm just mentioning that. But these are all methods by which you can configure containers. Okay. What this also says is there is a lot of flexibility, but also a lot of complexity. If you are a user, you want to create a container, you want to think now, should I use a credit-based scheduler? Should I give hard limits? Should I use a share-based scheduler? What makes sense? Okay. There is no right answer. It depends on what are you going to run inside your applications, what performance you want to see, and so on. Okay. So a lot of different knobs, but now it's left to the system administrator and users to figure out how to use it. Okay, no one is going to tell you what is the right weight or what's the right fraction. You have to figure it out as a system administrator or a user of this technology. Okay, so that's also causes some increase in complexity because if you don't configure it right, you'll see performance problems. Okay? Yes.
So for share-based scheduling, how does one decide that which container is going to get a higher weight than the other?
Okay, question is for share-based scheduling, how do you decide which container gets the higher weight? That is exactly what I said. It depends on the system administrator. The Linux is only giving you this mechanism. It doesn't give you any recommendations on how do you decide what is the right weight for any given container. So you have to decide how many processes will run. What's the aggregate CPU share that I need, and say, okay, that might need a higher weight than the other one. So that's the same thing in lottery scheduler as well. The number of lottery tickets you assign is up to the user. Okay, last question.
So in share-based scheduling, for example, if I have assigned 1 to 2 shares, but if first container is not working, then is there any default mechanism or like how?
Okay, so the question is the share-based scheduling. If you give weights and some scheduler does not, or some container doesn't use its share, what happens? Right? So share-based scheduling is always fair. As you can see, it reuses unused cycles and reallocates it. Okay? You never accumulate credit. It's use it or lose it. You have your share. If you don't want to use it at this time because your applications are idle, someone else gets them. Okay, so you will take all the unused cycles and redistribute in proportion to the weights to all active ones. Okay? That's a fundamental property of share-based scheduler. You never waste CPU cycles. Okay, so you will essentially have the fairness property working for you then. Okay. All right, so let's stop here and we can continue again next time.